Hi, everyone. Welcome to Training Tuesday, and thanks for joining our webinar today. I'm Heidi Reese. I'm the Training Programs Manager at Dayton Superior. We have an exciting Training Tuesday ready for all of you. But first, let's just go over a couple of housekeeping items before we get started. Just want to remind you that everyone who has joined the conference has joined muted so that there aren't any disturbances on the line as we present. But I don't want that to stop you from engaging us. Please feel free to do a question, in the question and answer Zoom area or chat functionality in Zoom. At the end, we'll have a mini question and answer session, and we can get those answers for you. Also, every one of these webinars are recorded and placed on Dayton Superior's YouTube channel, as well as daytonsuperior.com. So simply search for Training Tuesdays and you can see all of the past webinars. So this presentation is intended for training purposes only. Any of the products that we're going to talk about within this webinar, please go out to daytonsuperior.com or hkties.com, and you can get the safety data sheets, the technical data sheets, all of the ways to use the product. It's very important to read on that. We are just hitting on a training for now. All right, who is Dayton Superior? We are awesome. Can I just say that? We're just awesome. Chuck's nodding his head. We are the leading provider of engineered solutions. So we do offer that value add for you. Not only do we have the products of accessories, chemicals, forming, but we have the largest engineering team in the market, as well as standing behind our products with training. You're doing one right now as a Training Tuesday, but if there's anything that you need more of for training, don't hesitate to reach out to Chuck or myself. And you can do that at training@daytonsuperior.com. And that goes straight to us, and we'll get back with you shortly. Okay, so today, those value add services that I was referring to. We've got some engineering. We're going to talk about insulated wall panels for tilt up. We're finishing our tilt up month. We had TCA this month, so we'll be moving on to some other topics next month. We're going to be talking about delta ties and HK composite ties that achieve the maximum thermal performance within your building by using the unique system of combining those insulated panels and connectors. So, who is with us today? We've got Mr. John Osweiler, who is HK Composites National Sales Manager, as well as our very own Chuck Hoke, National Training Manager. Both of these guys are awesome with Dayton Superior. I'm going to use the word awesome 10 more times today. What do you think? Maybe we should have a Coca-Cola drinking game, every time I say that word. So back to John. He grew up in Iowa, so of course, when the time came for college, he attended Iowa State University to get his degree. He has been in the construction industry for 30 plus years, mainly working within insulated concrete wall areas and the insulating concrete form and sandwich panels. He is green building certified as a LEED AP BD plus C credential. In addition, he is an ACI tilt-up technician, and he is here to teach us about HK composites, specifically around the tilt-up. And we're going to hear from him first, but I'm going to go ahead and introduce Mr. Chuck Hoke. You guys have heard from him in the past, I'm sure, but he's been hanging out in the concrete construction industry for 49 years, where he spent 20 of those years dealing in accessories, forming, and chemical products, notably 29 of those at Dayton Superior. He's got diverse roles in the past, including the product management, and he's got that business and civil engineering degree that really positions him as a subject matter expert, doing the engineering, and just all those years in the industry, he knows his stuff. So with that, John, take it away for us.
Thanks, Heidi. Appreciate letting us do this again. We've done a couple of these presentations, including include sandwich panels. The last one we did was a little more specific to the precast market. Today we're kind of weighing things a little bit towards the tilt up side of things, which is also could be called site cast, which is what I say a lot of times. In specifically what we're talking about today, oh boy, there we go, is insulated sandwich panels and how we go about making that happen in the most efficient way. So when we talk about sandwich panel, we're talking about two layers of concrete. We call them withes with insulation in the middle. What's important is that we make that efficient, and that when we're insulating these concrete walls, that we do it in a way that we're getting every benefit we can out of it, that we're just wringing every economy we can. So the thickness of insulation varies depending on the facility type and what we're doing in there, as well as the actual makeup of the panel itself. There's really two primary materials in a sandwich panel. There's a few more than that, but there's really two main ones. That's the concrete and the insulation. There are no cavities within this wall. This is not a cavity wall system in any way. There is reinforcement in that panel. There's rebar. There may be some wire mesh depending on the panel type that we're doing. But again, no cavities. And this can be a completely finished, efficient, complete panel, even without any coatings. This is a barrier type of system. So there's no rain screens. There's no other waterproofing. There's no air barriers or vapor barriers that are needed in most typical panels. That can change a little bit if we get into freezers and coolers. But in this case, it's these two materials, and anything else we do to it, whether it's coating it, thin brick, or anything else, any kind of architectural accents, that's just aesthetics. So we can do wall panels, sandwich wall panels, really in about any size. It's pretty much the same as what we do any other type of tilt-up wall panel in terms of sizing. The insulation can be pretty thin, or it can go up to some pretty significant thicknesses if we need it to. These wall panels have the two Ys can do different things. In most cases, for site cast tilt-up applications, we have this style where we have a structural layer or a structural withe, and that's the load-bearing withe. It is almost exclusively on the interior side of the facility. You'll see why we do that here in a couple of slides. And then we have a non-structural withe, which is the face. And that face can be as thin as 2 inches if we really want it to be. It could even be thinner than that, but typically it's around 2.5 to 3 inches thick. That non-structural wire, that face, isn't doing anything except protecting the insulation and making it look the way we want it to look. So we can do this a couple different ways. Precast, obviously that's done at a precast plant. Oftentimes it's under roof. You have a lot of factors that can complicate things that are taken out of the equation when we do precast. Those panels are cast on beautiful beds, steel beds. They can vibrate. They can be heated if we need them to be. They'll batch the concrete in the plant, and then those panels are then shipped to the site on a truck. And then we have the tilt-up, of course, which is site cast on the facility floor if we're lucky. Most of the time, we like to cast these panels right where they're going to be tilted into position. Doesn't always happen that way. Sometimes we need to cast them a little ways away and walk them with the crane to their final tilted up resting place. Any type of facility can be done this way. Right now, probably in terms of total square footage, we're doing so many data centers that it's really pretty remarkable. But we can also do just about any other type of facility, from correctional to office spaces. It's amazing the architectural things we can do on these, not just the big box gray warehouses that you might typically think is what we're limited to. So here's where we start to separate how these walls are done. And we have non-composite wall panels, and we have structurally composite wall panels. So the non-composite panels have that structural withe to the inside, which is on the left side of the screen. That's the thicker one. That's doing all the work. And then the face is out there hanging by the connection devices that we're talking about today. And those connection devices need to be able to handle the weight and all the different forces that are put on them, both when we lift the panel and when it's in service. The structurally composite panels are a little bit different in that we have the two layers, the two wides of concrete acting together to bear the load. So we need a connection system that is both non-conductive, thermally efficient, and that can handle those loads at the same time. We save concrete thickness when we do it that way. So the non-composite panels, like I said, have the structural withe. These withe connectors that you see on the bottom right are made specifically for non-composite panels. They allow the face to expand and contract and move relatively independent of the structural withe. And on composite panels, we have to have a connection device that's significantly stiffer and stronger so that we share that load between the two. So the reason why this is important is on a typical non-composite panel where we may have, let's say, a 8-inch structural withe, and then let's say a 3-inch face out there, that's 11 inches of concrete. Well, we can very easily do the same thing, maybe in 2 layers of 3 or maybe 2 layers of 4. So we can do with 8 inches of concrete on a composite panel what we're doing with 11 inches of concrete on a non-composite panel. There's pluses and minuses to both of them. This is almost exclusively used, not exclusively, the precast industry almost exclusively uses the composite design of panels. When we get into the tilt up side of things, that's where we start to see we're kind of sharing things. No matter what style of panel we're doing, composite or non-composite, what we're looking for is monolithic insulation. We're trying to avoid any thermal bridges across that panel. The connection devices do that in and of themselves. So we've got kind of 3 connectors that we're looking at here: a composite, non-composite, and then the delta tie, which actually can do both. But we're looking for insulation to go all the way to the edges of the panels, all the way to the edges of openings, whether that's windows or doors or whatever it might be. And that's going to give us a lot of benefits down the road here. And we'll kind of show you why this is what we're trying to do. So when I say edge to edge, I literally mean that. So the edges of the panels, we dead end the insulation all the way to the edge. You'll look at the roof parapet detail there. This is really important. A sandwich panel makes it very, very easy relatively easy to match up the insulation, let's say from the roof to the wall, and really have that total envelope there that's insulated, where we don't have spots where we might have thermal migration or vapor transmission through that panel. So you're just looking at a couple different indicators of how we go about doing things. These are really simple ones. Some of the details can get relatively complex, but we're here to help design those. If we don't do it the right way, let's say on the left of the screen here is showing an outside corner, which is detailed correctly. If we don't do that right, you can end up with a condition that you see on the right, which is where faces moved and they weren't allowed to move and independently of another part of the panel. And then we have things like this where we have thin brick that started to fall off. In this case, you can have things happen like we might be overnight, it gets cool, and then in the morning, let's just say it's Phoenix. In the morning in Phoenix, you get that east sunrise, and it very quickly heats up the east side of the building. Now you've got those faces that want to move quite a bit, but the other side around the corner isn't, and we have a lot of differential movement there, in addition to just a lot of movement in general. So that's why we want to detail these things correctly, to let those faces do what they want to do due to thermal expansion, and yet we have a solid panel. We're thermally isolated from that outside, and just gives us a lot of other advantages too. When we're placing the concrete, we're trying to avoid a few things. Like I said, solid sections are a no-no if we can avoid them. Sometimes seldom happens, but sometimes we have to have a solid section somewhere, but it's pretty rare. So we're trying to avoid things like you see in this picture. Part of that happens if we're fabricating the foam in the field and we're just trying to move too fast, or locations of openings change, things like this can occur. We just got to get that foam down, and we got to keep moving and shaking and getting the mud poured. But we end up with things like this. There will be cracking in that area if it stays. We also want to make sure that you take advantage of what HK and Dayton can do in terms of design of the insulation system for each panel. So let the architect and let us determine those details. We'll cut it for you. We'll fabricate it. You get it on site, and you don't have to make any of those decisions. So this is an example of the tilt system going into place. If you're not familiar with it, this is just a representation of how we pour a site cast panel. So they're all formed up on the slab. That's where we want to see these things go for most efficiency. You've got openings blocked out. We lay down rebar, and now we're going to pour the structural layer of the panel. Or I'm sorry, the face of the panel. This is wire mesh. I got that backwards. So that's the face. Let's call it 3 inches with wire mesh in there. And then the insulation goes down. It's already cut. It's already fabricated. They just kind of lay it down, kind of a paint by numbers kind of thing. Just every sheet is labeled. And you have a map of where those go. They've already got holes in them for the connectors. So nobody has to think about where they go. You just stick a connector in its spot, and you're good to go. Once all that's down, then we lay the reinforcing steel, because now this is going to be the structural wire that's getting poured. What you're seeing here is we do some vibration to make sure we get good consolidation of the concrete in those connector embedment areas. Down goes the steel reinforcement, again, structural layer. So this does have rebar in it, just like any other solid panel would. And then we're done. So the lifting inserts are in place, brace inserts are in place, and then just representation of the panel getting put into place. These may not be done right and exactly where they need to be. We may have to have a sacrificial mud slab somewhere off the site. If we're doing, let's say, a school where you have a lot of stub outs for plumbing and all kinds of different things, maybe the slab isn't a place where we can pour panels. Well, we can do them somewhere else. We can stack cast them. We can do lots of things to make it as efficient as possible. Then I've been talking about 2 different systems, composite, non-composite. There's a couple different ties for that. Chuck's going to talk a little bit here about the Delta tie, which has been part of Dayton Superior for quite some time. He's got a lot of experience with that. So I'll turn this part over to Chuck.
Thank you, John. So with the Delta tie was originated originally by Dayton, especially in the mid 1990s. And what you're seeing is this is a non-metallic, non-geometrically configured 2-dimensional truss system, which basically is basically a monofilament strand embedded in an epoxy material, alkali resistant resin.
That's a lot of words there, Chuck.
Yeah, it's a lot of words there. Yeah. So basically it allows for no thermal bridging within the structure, provides composite and or non-composite action, no effect from ultraviolet light. So basically if it's exposed, it's not going to be a problem for it to be exposed for a while. But typically one of the reasons Dayton Superior originally came out with this system was we didn't sell insulation. So we allowed the customer to then determine what insulation type they wanted to use, whether that's a polyisoanurate, extruded polystyrene, or an expanded polystyrene. Any of those were all acceptable insulations that could be used with this system. Typically, by using this geometric shape, we basically lowered panel costs, unmatched spacing. This system here, requires fewer ties than any of the other systems within the marketplace. And we typically have two sizes. The standard size for insulation up to 4 inches is the 5x7. Basically, you are required to have 1.5 inches embedment, whether it's in the facial width or the structural width. As John explained earlier, what those widths were, it's basically the layers. So you basically need to have 1.5 inches of embedment in either side. And then because of the freezer structures, et cetera, there's a lot of structures are coming out with some 5-inch and 6-inch insulation, even up to 8 inches of insulation. We had to develop what I'll call a superior delta tie, which is basically just a bigger one. It's 9 by 11 inches, and once again, it's all graded on how much insulation you have as to which size you actually are going to be determined, and also the orientation of the anchor. As I talked about the orientation of the anchor, it's designed primarily just to get that 1.5 inch embedment. So for up to 2 inches, you can lay it on its 5-inch side down. When you come to, on a 7-inch side down, and if you have to turn it up or anything up from 3 inches to 4 inches, you just turn it 90 degrees and use it in a vertical position. The spacing remains the same. So, and the same thing would be for the XL version. So, installation on the delta tie is very similar to that of the HK tie system. Basically, you're going to pour your facial width, which is usually the facial width is poured face down first, because your outside of the building is typically always poured on your casting slab. You then apply the insulation in place here, and then come in and slide the delta tie in the joints between the sheets of the insulation. And you're going to basically muck it in to get your 1.5 inches of embedment into the concrete. And once again, once you're done with that, you can actually then move on to your next row. But typically you are getting the same type of mass wall effect within, whether it's the HK or the delta tie. Reduces daily and seasonal temperature swings. Excuse me. And then concrete has a high thermal mass due to specific high heat and density. So with that, I'm going to turn it over to John.
Oh, thanks, Jeff. Yes. Yeah, so you can see there's a lot of similarities between the two, or between the three types. The delta tie allows depending on spacing and configuration, allows for its use both in composite and non-composite panels. But like Chuck said, in the end, we get the same thing. We get a thermally efficient wall where that mass is isolated on the interior, and that gives us great benefits. What you're looking at here are some images of why we're trying to control that thermal bridging. So when there's metal connections being used, say in the precast industry that uses them a lot, we have thermal bridges across that panel, and that's actually relatively significant. It doesn't take a lot of cross-sectional area steel or even stainless steel to give us some issues. But also, when we use lesser tie systems, a lot of times engineers will have to engineer in solid sections, let's say around openings or at bases of panels, at the parapets, that kind of thing, because they just don't have the strength in the ties to do everything they need to do, and that causes problems as well. So when we have that thermal bridging, we're really wasting part of what we're doing by insulating those panels. When we have that thermal bridging, we also have other things that happen, like condensate formation inside the building. The lower right image, for example, was a dormitory down in a very humid part of Texas. And those are cladding panels. And you can see the red at the base of all those cladding panels at the floor locations. And they have solid sections and metal ties, conductive connectors. And what happened inside that facility was they'd have condensate form down there at the floor where the panel meets the floor in all these rooms. And that's a pretty big issue. We've also seen that happen in panels on hospitals and stuff like that. So it's a big problem. It's not just energy efficiency. It's not just controlling cracking by letting the face move. It really is about much more than that. And water condensate is a big enemy to any construction method. Every project we do, we can also show you a dew point analysis of that particular panel for that particular facility in its area where it's being built. So we can give you an idea what where that dew point is going to lie. Little secret here, even though we do typically much more than 2 inches of insulation, as this industry has progressed, we're seeing more and more insulation because people want even more and more efficiency. But little secret is 2 inches of insulation in a typical non-composite panel works quite well in just about any part of the country. And I'm talking from Alaska to Florida. We can do a dew point and show you that that is going to perform pretty well, or actually very well, in any part of the country. So you could take the same panel from Maine to Alaska to Florida and have no issues due to vapor drive or anything like that. Once we get into low temperature facilities, that all changes quite a bit. But
Hey, John.
that's how efficient these are. Yeah.
Don't mean to interrupt you, but I do have a question.
Yeah.
With the fascia panel being encapsulated with forming around the edges and the foam insulation on top, are there any differences in curing and the strength gain between the fascia and the structural panels? Do you want me to repeat that?
Isn't that a good question?
It's from our chemical guy, so I hope so.
Okay. So when we cast the face down on the slab, of course, all the chemical guys have their own things that they do, and the chemical side of things is not my area, but you've got curing agents and bond breakers and everything that go down before we cast that face. That's what keeps it from sticking to the panel, because we are casting directly on the floor slab. But so we're casting on that slab, the face, and then as soon as that is poured, we're laying down the insulation. So now we've got a very advantageous curing situation for the concrete. We're not losing water due to evaporation. We're insulating it, so if it's cold outside, we've got that help with us. If it's hot outside, it can obviously kick those temperatures up pretty quick. So we need to work fast when we're getting connectors in. But it's a very ideal situation for curing that face. I think is what the question was. Now, from on the structural wise, it's pretty much typical of what you would normally see. We are casting then on top of the insulation, which means we're not really going to lose any moisture to that as you would, let's say, if you're casting a floor on rock or on sand. But so they're very good. They're very good situations for curing those panels for sure. Yeah, work for me here. There we go. In addition to all the other things we talked about, ICC, for example, recognizes in its codes how efficient the mass effect really is. So let's just look at, just for example, the left box in, we're talking about climate zone 2. in the left box, and you'll see a mass wall, meaning in this case that applies to us, a sandwich panel. For your facility type, you're going to need an R 5.7 of continuous insulation, CI, continuous insulation. That's all you need. If you go down to wood framed and other type of facility, you're going to need an R20 between studs, for example, or between steel studs. And then you're also going to need, an R20, or you're going to need an R 3.8 continuous on top of an R13 in that wall. Or let's just go to a metal frame building. You're going to need an R13 plus an R5 continuous just to match that R 5.7 performance in the mass wall. That's how effective the mass is. It's also an incredibly tight facility. You have no wind intrusion, you have no rain, you don't need any of those additional things, because this panel is such an effective barrier system. And you can look in the different zones as things change a little bit, but you can see that your continuous insulation is very effective when you have mass combined with it. Anything else needs both. You need something between the studs, something in that cavity, plus continuous insulation in addition to that. That's hard to do in a lot of different facility types. Whether it's Delta tie, HK ties, we can give you everything you need for those panels kind of tied up in a bow. So we'll give you layouts for the insulation. We'll fabricate the insulation. You will of course get that in addition to the Dayton lift and brace drawings. You'll get the reinforcement plan, all that kind of stuff. We can help with that and put it all together for you. We'll do the dew point analysis. We will also help. We have our own engineering staff, of course, and they can help the designer or the builder with any specific issues they might have, whether it's special details that we need to work up for special conditions. We're there to help, and it's really important to us that these things go very successfully, because if something happens on site, we are usually the first ones to hear about it, and we are the ones that are looked for solutions. So we'd rather have everything go perfectly from the get-go. In addition to that, we like to be on the site when these panels are cast, just to make sure everything's going pretty good. We always remind people that, we're casting in something where those ties have to be consolidated very well, and timing is an issue. So maybe we need to think twice about what the delivery schedule for the ready mix trucks are, that kind of thing. So we're there to help. We have plenty of people to affect that help, so please use us in that way.
Thank you, John, so much. And we do have one question, and guys, we're a little over, but please put your questions in if you have any. Here's one. As the concrete cures, how much condensation or moisture ends up in the insulation? And then the second question is, does the insulation material matter?
So most of the insulation, the majority of the insulation is extruded polystyrene, which is extremely hydrophobic, and it really doesn't take on moisture from that application. Liquid moisture, it just really doesn't infiltrate the panel or the panel insulation. There are some other insulations we use, polyiso. We have to be careful about how we use that it has the right laminates on it in order not to take on moisture. But where insulation and moisture are typically start to cause problems is from vapor drive. And that can inundate with high humidity inside some insulations, and then give some problems if it doesn't have the ability to dry. But the casting process is not an issue in terms of taking on moisture within the insulation. And the other question had to do with curing. I can't remember.
Are you there, John?
Yeah, can you hear me?
Okay, yeah, sorry, I think
Yeah,
it
I'm
cut out.
sorry. I forgot the second part of the question. I apologize.
Oh, no, no, no. Let me see here. We actually got a couple. I'm so excited. Um, the second part is, does the insulation material matter?
Oh, yes and no. The primary reason it matters is there's different R values per inch in different insulations. So extruded polystyrene typical is an R5 per inch. Polyisos are going to be anywhere from 6.5 to 7.5 per inch. So it kind of depends on what the R value is that we're looking for. Cost is a factor. Expanded polystyrene, which is the beadboard type of stuff, that's a little bit lower R value per inch, but it's less expensive. So there are times when we really care. If we're doing freezers, for example, my concept is that we want as hydrophobic a type of insulation as we can get. That would be extruded polystyrene, but we use all three types: expanded, extruded, and polyiso in projects all the time. A lot of time it comes down to just what do we need for R value. Is it is it advantageous for us to use a polyiso, let's say, and cut back on the thickness for the same R value or not? It just kind of goes. A lot of times, it also depends on what the architect has specified in that panel.
Fantastic. Okay, so we have another question, but John, I'm gonna let you answer that off to the side since we're over. Just want to remind everyone that Tilt Up product are on special for the month, Superior Deals Month. It's only a couple more days. Tomorrow's Halloween, right? So you really got the afternoon and tomorrow. So get that in. Really quick, your resources are the hkties.com and DaytonSuperior.com, and you have access to all the information such as product information with the product pages, technical and safety data sheets, as well as any kind of handbooks or success stories. And most importantly, the contact information. Just click on the state that you're in and you can find who your dealer sales manager, as well as your technical sales manager and customer service person is. I guess it's an R. All right, with that, I want to thank John and Chuck for coming and helping us to understand the HK with the tilt. And Victor, we will get on your question answered off to the side for you. So look for that email later. Everyone have a great Tuesday, and I will see you next week. Thanks, everyone.